I think it's 2:01, Greenwich Meridian time. So just want to thank everyone who's attending this session and come to listen to our 5th Groundwater Youth Network webinar. So it's growing and growing, which is really exciting. Today we have a wonderful presenter. So we have Kshitij Sahal, I hope I'm saying it right, who is from Nepal. And I'll just give a little bit of background and then I'll hand over to him. So Mr. Dahal did his undergraduate in Nepal and is now a PhD researcher at Arizona State University. He has been specializing in integrating artificial intelligence with remote sensing to study the Earth's critical zone. So his research primarily focuses on analyzing surface and groundwater using remote sensing techniques, understanding the role of AI in earth sciences, and leveraging AI for improved decision-making processes, as well as utilizing AI for the accurate prediction and effective management of environmental anomalies and their impacts on hydrological systems. So all very interesting work and very modern, using AI, which is something that's become more and more prevalent in our societies. He has also contributed to over 10 peer-reviewed articles, so very academic and very impressive. Outside of his PhD work, he is on the editorial advisory board for the Journal of Regional Environmental Change and is also additionally a Groundwater Youth Network member. So that's Mr. Dahal. So he will be presenting today, and you can see on the screen, on machine learning and groundwater potential mapping with explainability. So if we could keep questions to the end, or please do pop any questions in the chat pane and we'll get to those at the end. The chat pane is open to everyone. And yeah, so basically, yeah, over to you. I'm really interested to hear the talk.
Hi, Georgia. Thank you very much for the introduction and also for inviting. Hello, everyone. Good morning, good evening, good everything wherever you are. So I'll talk about machine learning, as Georgia said, in groundwater potential mapping with explainability. So I'll focus more on explainability part and also cover some of the applications of machine learning that we did for groundwater potential mapping. By the way, you can also get these slides if you are interested with this. I can also share this slide with Georgia and hopefully they can share with you. So this is agenda for today. So I divided my presentation into 2 parts. So first, I'm going to talk about groundwater flow models, basically groundwater potential mapping for 10 minutes. After that, I'll shift to model explainability. Essentially, how do we explain these groundwater potential flow models? And if there is enough interest, we will do our demo. Hopefully, we can do it in 5 minutes. So I think it can help because we can visualize and we can change it. So I have a Google Colab link that I will share at after this first 2 parts. And then we will go to Q&A, but feel free to post your questions early in the chat box. So we'll start with the groundwater potential modeling. So there are different kinds of models which are needed, and there are different applications as well. It depends on what kind of data we have and what are our interest. So most popularly, there are numerical models, which are like ModFlow. Those are numerical models based on the program ModFlow, and there are graphical user interfaces. So it includes system definition datasets from geology and hydrogeology, both to define the area and then convert into grid and solve this. These are better models, I would say. And there are other statistical models which are also useful, but these are not as deterministic as numerical models. And what it does is it compares, it kinds of give information about the relative groundwater potential in that catchment or in that area of interest. So here on the right, you can see a map that has 4 colors from red to blue. So what it does is it shows within that catchment, it shows the level of groundwater uh, in different ways. So the red ones are very poor groundwater potential zone. It means that the groundwater is not readily available yet here. And on the blue colors, it is relatively better. So these are not represented by the height or anything, but it shows the relative importance or relative availability. So these are very naive ways compared to the numerical models. We can define this as a groundwater potential as function of the terrain, geology, or climate. So mathematically, you can represent something like this. So the idea is the terrain, for example, elevation, slope, or the different curvatures, that gives information about this because the hydrological process will depend on these terrain factors. So these can help us understand where the groundwater is. And the y here is the output, which is the probability of groundwater being high or low. So if the probability is 1, the groundwater potential is high. If the probability is 0, the groundwater potential is very low, but we have probabilities in between. So that's where these classes come from: high groundwater potential, medium groundwater potential, and low groundwater potential. Interestingly, there is increasing interest. So this is a recent paper in Journal of Hydrology about using these kinds of models. There is a very nice review paper if you are more interested about it. But uh, I see that publications are increasing over different areas. So I think these are useful for decision making. Also very interesting, I found that these terrain-based methods, because it gives some sense of if there is water or not, these are also used in exploring different planets like Mars. And a figure on the right shows a picture that looks like a spring. And maybe scientists are thinking about if there could be groundwater or something like that in the past. So these methods are helpful. So this is overall summary of the methods that different people have done, again from the same review paper. So essentially, what they do is they collect a lot of data sets which can represent the terrain condition, the climate, for example, rainfall, and lineament density. These are density of the lineaments, which are like rock fractures. And this gives information about these are the different features, and we can train models, different models. There are plenty of models available, and it has been advanced over time, but there are different models, and we can use those models and try to predict again these probability of groundwater zones, and we can convert those into different classes: high groundwater, low, or medium. And these are helpful in our decision making and resource planning for groundwater development. So for our study, we did this in Nepal. So these are 5 catchments shown in the figure here. This is the inset is a map of Nepal, and this is the zoomed in version of that. And we have 5 catchments. The reason we choose these catchments are there is an interest of understanding groundwater levels here, and we do not have a system definition data here or groundwater flow models like ModFlow. So that will require a lot of data. So we thought about starting with the statistical model and see what we can understand from here. So to represent groundwater potential high or low, we need some basis to do that. And people have tried different methods. The best method, I would say, if we have the level of water in wells or some measurements like that, that becomes very easy because we know how deep the groundwater is or the water table is from the surface. But often in mostly remote areas, it is not readily available. So people have used these springs, which are the origins of rivers, as a high groundwater potential because theoretically it is easy to understand that springs usually originate from groundwater. They can originate from others too, but springs also represent a zone where groundwater is transitions into surface water. So these are used as the location of springs or the origin of rivers. These are used as high groundwater potential zones, and those are used as low groundwater potential zones. So that becomes our classification problem. So I was talking about these different variables. So these are the variables we use, which are very similar to the paper I showed earlier. And this is our target variable, which is spring and non-spring. So here, blue dots represent spring locations and red dots represent uh, the non-spring location. And what we are trying to do is we are trying to use all of these features and create a model that helps to classify this spring and non-spring. And the idea is that because there is presence of spring and there is not presence of spring, there should be some difference in terrain or geology or a climate condition that actually makes this difference. And we're trying to understand that to understand groundwater assessment. So the first step we do usually in machine learning is multicollinearity removal, because these features can be correlated to each other. And if we use all of this, there can be multicollinearity effect, and this actually makes model poor, and also uh, it makes model complicated to explain. So we remove this multicollinearity. There are many methods, but we use this variable inflation factor, and it is recommended that a value which is more than 5 is removed, because it has multicollinearity with another feature. So we got reduced number of features which essentially represent the same without losing much information, because they are correlated. So then we train this model, the groundwater potential Y as a function of terrain, geology, and climate conditions. So that becomes our X, and the groundwater potential becomes Y. So we are trying to fit a function in such a way that represents this probability of groundwater. And we evaluated this model. So this is a pretty standard thing. We evaluated this model using area under the curve, ROC curve. And we use two models here. I'll talk about these models in a second, but we use two models just to compare their performances. And so this is ROC curve. Usually the curve should be, let me see if I can. Okay, so the curve should be straight line if it is perfect. It should be a straight line that has 0 false positive rate and higher true positive rate. That should be 1 for the ideal model. And if it is like this 45-degree line, which is red line, it is a random guess, or better, not better than the averages of all the data point we have. So this shows how accurate our model is. And usually there are standards that if the area under the curve is more than 0.9, that is considered as a very good model. And if it is more than 0.8, it is considered a good model that can be used. So we found on the both models we tested, it's around 0.87 and 0.88. So which is very close to very good. So we suppose it is good. And this is the result we got after training the model and evaluating the model. So these are the 5 catchments I saw earlier, and this is the groundwater potential. So it has 3 classes because it is classified into these classes, but the outputs were earlier in probability format that I showed earlier. So here 3 colors are represented in this plot. So red areas are the low groundwater, relatively low groundwater potential zones. Yellow areas are relatively medium groundwater potential zones, and these blue areas are high groundwater potential zones. So when we did this, it also matched our intuition about what it should look like. So we thought it is good. So there have been long interest of doing this, and it's because it's a machine learning model, it's very difficult to explain why some areas are low and why some areas are high. I told earlier that it depends on the terrain, geology, or the climate conditions. But after training the machine learning model, because we do not have a function to define it, it becomes very difficult. And the problem is, while making decisions, it's very difficult to make decisions without these understanding. So now I will shift to the model explainability part to understand how we can use model explainability to understand these. So there is a growing interest in explainability because these are needed, that we also know. And there are many methods, but I have overview of these methods. There are also new methods like physics-informed neural networks or Bayesian approaches. But I'm going to talk about two methods that we have used. So there are two methods. One is model specific and model agnostic. So model specific is a way that you make your machine learning model in a way that it is explainable. And examples are like generalized linear models, logistic regression, and generalized additive models. So I'll talk about that later. And then there are also model agnostic methods, which are like first you make your machine learning model, and then you use some kind of technique to understand or explain these results. So the model itself is not explainable, but we use some ways to explain it. So this was our approach. So we collected string and then conditioning factors or features, and then we use these two models, EVM and GWYN. So EVM is explainable boosting machine, which is based on trees like random forest, and GWYN is neural network implementation, and both are generalized additive models. So the reason GAMs are very useful is because there has been a trade-off between accuracy and explainability. For example, if you're familiar, machine learning model like boosted trees or random forests are very accurate compared to others, but they are very hard to explain. And also like models like logistic regression, decision list are very easy to explain, but we do not get that high accuracy on this. So here GAMS comes to help. So it has the highest accuracy as boosted trees and also the explainability as decision list. So we can at the same time get the higher accuracy and also get the model explainability. So that is helpful. So how they do it is, this is the equation, looks maybe scary if you have not seen, but it's very similar. So the GAMs are different in a way that they train each feature one time. So for training one time, they use one feature and try to predict the output. And they combine the effect of all features so that it becomes a machine learning model of multiple features or multivariate, but at one time, it takes one feature. So this is the difference between other machine learning models and these machine learning models. And turns out it works very well. So this is a tree-based implementation of GAMs, generalized additive models, which are essentially adding the contribution of each features to make a model. And so these are very similar. If you see this equation, these are very similar to we do in linear models like y equals to mx plus c. So here we remove this mx with the function, and the idea of machine learning is that if we train with enough data, it can represent any function. So we use trees to represent these functions over each features and then sum everything up to get our model output. So this is a very I think it helps to understand more. So for example, if there are different features like x1, x2, x3, or up to xn, then in explainable boosting machine, what it does is instead of making a tree and trying to fit over different features, it creates trees for each feature. So this is a very simplified representation. This tree can be very large, that has many logic. if this happens, and then if other thing happens. So that goes like this. So what we do here is we create this tree for each feature that kind of associates our output with feature, and then we keep improving it using boosting. Boosting is a technique of improving the model, and then at the end we get this plot, which we call it partial dependence plot, because it is showing the partial dependence of groundwater potential to that feature. For example, let's say slope or elevation or precipitation, and this gives relationships. So now we remove all these trees because it's not needed, and these graphs are our machine learning model. So it looks like this. So this is what we got. For example, if we go over slope, it shows that the score is positive or negative. So it becomes a sum of, so it becomes a partial dependence. For example, we are going to sum all of this. So this is the contribution of slope. So it can be positive or negative. So if it is positive, we can say it is helping that area to become high groundwater potential. If it is negative, we can say this slope is not helping or impacting negatively for the groundwater potential. So we found this interesting relation that up to slope 30°, which is not very steep, are actually good for groundwater potential. And after 30°, it decreases, it impacts negatively. So if the area is very steep, the groundwater is likely to impact it negatively. So, but this is not the all explanation. This needs to be combined with all of these. For example, lineament density or other variables like elevation, also precipitations. So other cool thing about this is once we get this model, and we can also visualize this model, because these are graphs, these are vectors, we can actually use our human understanding and update this. So this is the advantage that these kind of model have. So if we know the relationship should be something like increasing or decreasing, we can change it. So I think that is cool, because the other machine learning models, which are black box, we don't know what functions are doing and what kind of relationships are established, and we cannot edit them. But these models, we can edit them, and there is a package called game changer. So we will do the demo of this. So we can actually include our human understanding to align these machine learning models, and I think that is helpful. And also this is helpful when the data is not available or the full distribution is not represented in the data. We can use our understanding and we can update what the distribution should look like. So now I will switch to other method. So that was the method I was talking about, was how do we make our machine learning model explainable, model itself. So this is the method which is agnostic to the model. So this can be applied to any model theoretically, but implementation may be not available for all of these models, but most of them are. This is called SAP. So this comes from game theory that essentially try to understand what is the contribution of each player to the score. So this equation has two parts. It looks difficult, but it's actually very easy. So the first part shows the combination of different features, and the second part shows the marginal improvement of output having or without having that feature. So it measures what is the advantage of having that one particular feature, for example, slope. So what slope can help in the model, and what is the contribution of slope, and it check over all of the combinations, so it becomes a complete explanation. And this is what it looks like from SAP, which is very similar to the partial dependence plot I showed earlier. And we can relate, for example, lineament. So we thought this was interesting because we found that a negative, so this plot is, if you have seen this for the first time, it has many things, but what it shows, if we go on lineament, if the color is green, So it shows it's on the left side. The impact or the score is negative. It shows the lower value of lineament. This is actually lineament density. The lower value of lineament density is not very good. So it means if there are no rock fractures or lineament geological features, the potential of spring is not very good. And that matches our understanding that if there are fractures, so the water can move through that and the spring, we can see spring there. So these also helps to verify our model that our understanding is aligned. So that was for the all of the areas, but we can also create a one particular explanation. For example, we are interested in particular one area or planning something for that area. We can check what is contributing to that very area and what is controlling that area, basically. So it's not cause and effect, but it is kind of association. Cause and effect would be more difficult, but it also gives some sense of it. And we see usually we think that the highest contributing factors contributes most in all cases, but we found that that's not true because in different geographical location, there could be different variables that is contributing. For example, there are 4 plots in A, because others are okay, but slope is very steep. It is 51 degrees, so it becomes a very low groundwater potential area. And in the second case, the elevation is not preferable. That's why it becomes low groundwater potential area. For the third one, other conditions are not very good, but the elevation is really nice, so it becomes positive. And in the fourth case, the bulk density is higher, so it means there is more water in the soil. So that means there is a good groundwater potential on that area. So we found that, and we also third that this is interesting that different variables can control different areas. And in terms of map like groundwater potential that we are doing and other geoscience applications, we think the explainability should be done locally instead of trying to understand the model. So there is also other very cool thing I wanted to share. So this is a talk to EVM. So we can actually ask when we make the prediction, we can ask the model why you predicted that. And it can answer because that area has this feature value of that, and that impacts like this. So for example, if the slope is very steep, it promotes runoff, and that becomes very difficult to recharge the groundwater zone. So it is likely that the area is very poor in groundwater potential. So it can explain like that, and you can use this model. I think these are very useful. Maybe not in research, but maybe more into businesses or decision making or policy. I think this is very helpful, and it also can talk in these using these language models, so which is cool. So I will go over it quickly. So I told about gaminate. So the architecture I was talking earlier was about trees. So trees were very popular, but now it seems like the neural network are very useful, and they are especially useful with lot of data. So this is a similar idea. So it also takes one feature at a time and estimates the function, but not using trees. It is implemented using neural network. So very similar idea. And this is what it looks like. There is a link to the paper. So it creates a network for each feature. For example, in the main effects, it is shown that for X1, there is a different network. For XP, there is a different network. And we can have different networks for different features. And also we can include interaction effects, for example, 2 feature at a time. So how slope and elevation contributes together. So we can also model that using this interaction effect. So very similar idea. And this is the plot we got from this is the partial dependence plot we got from Gaminate, and which was very similar to the explainable boosting machine. So we thought because these models are different, which has one does work with a tree-based model, the other model is neural network-based model, and if they are very similar, it kind of gives our confidence that model is somehow doing good. And this is a comparison we did, and these are very similar with Gaminate and EBM model. And we thought maybe Gaminate is a little bit better because it has more cluster, and this is also aligned with our understanding that the high groundwater potential zone should be more clustered than sparse. So that was for the presentation. So let's quickly do a raise your hand if you are interested in demo, or you can also follow this using this QR code, or we will go to the question and answer round. Okay, I see some of the hands.
Yeah, people raising their hands. I think it'll be useful to do a demo if you're happy to.
Okay, cool. So let's do the demo. So you can also follow with me if you want, or you can see here and then try on your own later. So there is a document called demo. I can also share this in chat.
Yes, that'd be useful. Thank you.
So there are two things. So one is the data set that we have generated. So it's ready to use data. If you go here and download it, you can download it. So what it has is it has this bunch of features that we have used. And at the last, this has a column called presence. So the presence, it has 1 or 0s. And the second is there is a Google Colab link. You can click here. And I think it will show something like this. The reason is I uploaded it from my local computer. So if you do this, the option on the top. Georgia, can you see my screen?
Yeah.
Thank you.
I'm trying to follow along.
If you do this, you will get something like this.
I don't get Google Colab as an option, but maybe I have to search for it.
So if that's the case, the Google Colab, I think, is not installed on your Google Drive.
Oh, okay.
So
then
it's
otherwise
very easy. We can check.
Oh, it's easy. Yeah. Maybe for those who don't have it as well.
Yeah, I think instead of trying to install it, I think you can follow it here and then try on your own later. So trying to sorry that I had to stop sharing. I will do it again because I could not find the, okay, I found it. So it looks like this. So once you download this Spring dataset, you need to drag it here to upload it. This is where data will be, or you can connect the Google Drive later, but for now, or you can upload from here. So it's not very difficult. It's just one step, and you can. Yeah, I wrote this in the document. You can follow that later. So let's go over it. So first we install this tool package, which is Interpret. This has model and everything, and this is the game changer that lets allow editing these models. And in the second one, so it reads this file Spring, and then try to and separates the presence as our target variable, because that is our target variable, the groundwater potential. And there are a bunch of features which are our features. So that becomes X. And then we train this model. So it's very easy to train this model. So we just use EVM equal to explainable boosting classifier. That is our model. And we can give random state to seed. So this is essentially, so seed is 1. We can exclude this part. This is to recreate the model, because machine learning model can be different when trained on different times. So it is a good idea to include the seed if you are not considering about getting all the outputs and trying to figure out that. So it is training the model, because there are around, I think, 8 or 9,000 data sets. So it takes maybe 2 or 3 minutes to do that. And it's very fast, because it is a tree-based model, so it's very fast. So while it trains, we can go and look at this explanation. So when it trains the model, it becomes like this. So these are the bunch of different features that have been ranked accordingly. And we can go to this and check the relationship with each variable. For example, elevation. So if the elevation is very high or very low, so this depends on that area as well. The groundwater is negatively impacted, but it is around like maybe 1200 to 1900. It is impacted positively. So it depends on the area. And this is changing this model, so generalized additive model. So we can go here, and this is the editing environment. So for example, if we don't like something, for example, precipitation doesn't have a good relation. So we know that, we think that if the precipitation increases, there is more likely to have groundwater recharge. So that should help that area to become high groundwater potential zone. But it's not represented here. Maybe the reason could be the data distribution was not fully available, but we can change this. So there is a select option. So we can select like this, and then we can include it. We know that it should be increasing, so we can change like this. So now the model is changed, and we can see the impact here, how the accuracy is changing, how the area under the curve is changing. So it's not changing much. It means even aligning these models to our understanding is not decreasing the accuracy. So this is still good. And we can save these here, and then we can read that file here to actually update them. And then we can use this model to predict on all of the locations that I showed earlier. So let's see if it is trained. So the model is now trained, this EVM model. So I was training it earlier. It is now trained. So next step, I can use this. So that will come the same thing, because I already did it. So this is hot model found. So these graphs are the models, and these relationships are established here. And the other thing is we sample some data, and then we visualize these partial dependence plot, and then we can change them. So that's the thing I wanted to show in the demo. So I think that was helpful, and thank you
Very helpful.
everyone, and happy to take questions. Also, the paper is available in Journal of Hydrology. So if you think this is interesting, you can go and look over it. And if there are any questions, happy to answer. Thank you.
Thank you. So interesting. Really enjoyed the demo bit. Need to get my Google Colab so I can follow along. But yeah, super interesting. So thank you so much for presenting. The chat pane is open to those who have any questions, or if you want to unmute yourself, or if actually those maybe, or if you want to raise your hand if you want to speak. then I can unmute you. I think that's how this Zoom link works. So if you would like to raise your hand now or put something in the chat pane. We've got a chat question from Marwell Crystal asking, how can you show us how the maps were generated, or explain how they were?
Okay, so let's discuss here. You can see my slides, right, Georgia?
Yes, yeah.
Okay, so I think that's a good question, because we trained a model on a CSV data set and our map look like this. So the reason is these rasters that I have shown earlier are also numbers. So these images also have numbers, and these are the predicted values. So what we can do once we train the machine learning model, instead of using a CSV dataset, we can use a raster dataset that has the value of, like, in a matrix format, and it goes to each of the pixel. The model goes to each of the pixel and predicts its outcome. And then, because we have information about latitude and longitude, we can map it back to the raster, and that becomes our map. Hopefully that answers your question.
I have a question. So groundwater potential, these outputs, who's interested in them and what are they useful for? Is it normally based on a really large regional area, or can you use this type of models in really small localized areas?
So I think that's a very good question. So I would say this is useful more in regional ways rather than in local ways. But we've also found that there are some of the local effects that controls it. So it would be good idea to start with these groundwater flow potential models, and then go to the region of interest and make numerical models which are more deterministic and gives more information. That is recommended.
And the outputs, finding out areas that have greater groundwater potentials that can be useful for water supply, water management, or just general themes of.
So these can also be used for policy making about how much we should extract and which zones should be considered as recharge zones, which zones should be used for extractions. These kind of information can be not only from this, but these are helpful to decide and plan those things.
Great.
Especially when you don't have data.
Especially when you don't have data. Very true. And we have a question from Angel in Triago asking, have you tried to use the same approach for modeling nitrates, or do you think it is possible changing inputs like location of pollution sources?
Yeah, very good question. We haven't done something related to nitrates, but I think this model can be useful on that too. But especially if you have the data of or the model like ModFlow, then that becomes very helpful, because that also have velocity vectors and how it moves, so you can understand more transport and fate and transport of those things. So I see some of the applications, but we haven't done such thing here.
We have a question from Jason Pinther asking, for the EBM model, do we assume that the factors T, G, and C have the same weight? The general equation you showed assumes linear relationships with these, but with weights not mentioned, unless the weights are intrinsically accounted already.
Yeah, that's a very fair question. And yeah, you are correct that we do not need weights, because we replace this with functions. So for example, here, so we replace this with functions. For example, instead of having W1x1 that we usually have, W1x1 plus W2x2 plus W3x3 plus W4x1x2, something like that. So we remove that weight here and we just use the function. So this function will automatically take care of the weight, and not so weights will represent the linear relationship. With these functions, we can also represent these non-linear relationships. And these models come from a very similar idea of using weights and variables for the making the function.
Great, thanks. Got lots of questions coming through. Akram is asking about ground truthing. So have you ever gone out and taken field measurements to compare to what the model outputs were?
So we haven't done this. So the first thing is our data comes from field, which is spring locations that I have shown earlier. So these data were collected in the field. They were visited and collected that these spring locations exist there. And after generating groundwater potentials zone, it would be very useful to go there and get some heights information and understand what is low groundwater, what is high groundwater zones in those areas. But we haven't done that yet. Hopefully we can do something.
Mamona asks, how was the model validated? I guess in a way that's kind of similar to a previous question.
Yeah, ideal would be to go to field and measure it. But looking at the data and the relationships, so there are methods to do this. These are statistical methods. So one is ROC curve, rock curve. We can use this to kind of understand what is the true positive rate that model is predicting, what is the false positive rate that model is predicting. And we can get this on all of the thresholds, and we can get the area of it as our accuracy.
Great. And then Jason Pinter asks, and for the uncertainty of these groundwater potentials, are they accounted for in the ML techniques?
So very good question. These have uncertainties. So that's why we did these two different models to kind of compare two different architectures and what will the result look like if models are different and if we give the same input. And because these are predicted maps, so if both models are predicting, this is not the uncertainty analysis, but it somehow relates to uncertainty. So yes, we haven't done anything like uncertainty specifically, but we did try two different models to kind of create the consensus.
Sanjanathan, sorry if I'm not pronouncing people's names correctly, was very pleased with your presentation. Thought it was very interesting, and as asked, if you could provide an overview of the parameters and processes involved. But I feel like that's quite a loaded question. But I don't know if there's a.
Yeah, I think I can go here. So these are the bunch of features that we have used from elevation, slope, aspect, and curvature. So when the curvature is negative, means concave, so it promotes the recharge. So that area can have more recharge. And when the curvature is convex, the runoff is promoted, so it runs faster. So there is less likely to have the groundwater recharge. So those are our general understanding, which may not be true all the time, but we combine these different features, so it becomes a multivariate thing, and it becomes easier for the model to figure out what is the relationship.
Great. Raquel Neri is asking, how would you communicate this information to decision makers, and which model do you think would be best to be based on?
Yeah, I think that is a very valid question. So I did talk about it a little bit earlier. So we compared these two models, and based on our understanding that we thought that if the groundwater potential higher and lower zones look like this, it should be clustered because it doesn't go away in a very short distance. So we thought maybe gaminate provides better. But again, back to the earlier question, we need to actually go to field and measure it and verify which model is actually better. But these are very similar models.
Yeah. Crystal asks again, another question, which would this method be applicable to other climates such as tropical countries?
I do think it is helpful.
Mhm.
We'll have to figure out how it works in that area. So if you are doing similar, I would be happy to see the results, or if you need anything, yeah, we can talk about it. And if you need anything, yeah, I would be happy to help.
Mm.
It would be
I think it'll be
interesting.
useful if
Yeah.
maybe if I could if you would be okay, I could share your LinkedIn profile on the
Mhm.
chat, if that's okay. And so if
Yep.
anyone wants to get in contact or collab, um, I think I can try to get your details from me. I'll put it in the chat
Thank
just
you.
now.
I think I can go to
Um,
the other question.
yeah, you go for it.
Sensitivity analysis to the features parameters. Have you done something like that? So it's not sensitivity exactly, but so we haven't done sensitivity analysis, but this model is very similar idea to the sensitivity. So this part, the second part of the equation, is the what it. So in sensitivity, what we do is we see the changes in the output if we change the input by certain percentage or some in some ways. So this is very similar. This model is very similar, and the idea comes from the sensitivity. So we did this. And this takes account into what happens if that particular one feature is used or that feature is not used, and what is the impact on the model. And we got some of these results, which is very similar to the the sensitivity, I guess, but we haven't done anything specifically the sensitivity. So there is another question. Yep, you can get the PowerPoint, and I think you can also get the videos. So you can ask Georgia about it. Maybe she can
Mhm.
answer. Mhm.
I'm gonna try share the recording. I'm gonna talk about maybe putting on the YouTube channel if there's a YouTube channel. In terms of the PowerPoint, I'm just thinking if loads of people are interested, instead of having to email it to loads of people, you could maybe put it on the Google Docs page that you shared. Perhaps if people could get access to that, is that something you can do? Because if people have that link, I don't know how that works. Otherwise, if that doesn't work, people can share their emails and I can email it to people.
So the link to the demo is available here.
Yeah, so I'm thinking on the actual Google Docs or for the demo, if you could put the PowerPoint there so people could
Mhm.
download it like what they did with the Spring file,
Okay. Yeah, I can do
just
that.
because everyone has the link in the chat. But
Okay.
that's only
I'll,
if
I'll do
that's,
that.
yeah, okay, amazing. Yeah,
So
so
there
then
is
everyone
an
it will be
Mhm.
available on that link.
Perfect. There is another question about how much do we trust the data utilized in this says groundwater potential? Do you examine unsaturated zone and aquifer properties? So the short answer is we did not. We only try to use open source data sets because it's very difficult to get those data sets and it's not available on that area. So we use this open source data set, but we did try to include lineaments, and that was found very useful. And about the trust, I think we have to validate this. So there are ways to validate it. So there is also a saying that all models are wrong, but some are useful. So we should not blindly trust it and do everything based on it. But we can combine these to our decision making processes and try to understand what they mean. Uh, also talking about earlier, so we also need to go to field and actually measure it when we are doing some kind of interventions that is needed. But this gives us some idea of regional environmental condition, the controls and area. There is other question from Jason. Is the climate resolution of mainly of annual resolution? So about the resolution, what we did was, so this is also very standard. So we converted everything into 30 meters. So what it does is we don't have to compromise the resolution we have. For example, we have digital elevation model of 30 meters. So we brought back everything into 30 meters and we trained this so that any information is not lost. Have you also tried other correlation methods such as dimensionality reduction, PCA? So we haven't done anything like that because we thought that we use those methods which are very similar, which is very similar to PCA. So PCA tries to completely remove the multicollinearity, but that also makes principal components, which are again hard to explain because the principal components itself have equations of these features. So we haven't done anything about PCA, but maybe these can be useful to make these models better. Okay, so there are other questions too.
Not that I've seen. Yeah, we should wrap up in the next, before 3 GMT. If anyone has any questions in the last few minutes, please send them through. Otherwise,
there is
yeah.
I think last question, there is one from, can you use same technique to quantify groundwater resource and assess groundwater recharge? So I think it would be very difficult to get to groundwater recharge. That would be other processes, but this can be useful. I don't know if it makes sense. Yeah.
Okay.
I think that's it.
I think that's it. Yeah. Well, very interesting. Lots of questions from the audience, which is always great, which is everyone's listening and interested and wants to learn more. So, like we just discussed, Dahal put on in the chat pane the link to the Google Doc. So he will put the presentation on that Google Docs links at some point. And then I will sort the recording as well and then share where that recording is on our Groundwater Youth Network social media and LinkedIn platforms. So just, stay tuned. There you go. There we go. There's the presentation and there's his email. And I put his LinkedIn as well if anyone wants to connect with him as well. But yeah, thank you so much again. That was really, really interesting. And hopefully maybe some collaborations with others who are interested in this topic can happen through this network. So thank you.
Sure. Thank you, Georgia, and everybody.
Yeah. Bye, everyone.